Yesterday was I introduced to you the concept of supersymmetry, that it's a different kind of symmetry that is relating fermionic and bosonic degrees of freedom to each other. Yes, I gave you the algebra. It was a little bit abstract. So what we'll try to do now is sort of slowly try to actually build up a Lagrangian. Yes, we want to actually be able to write a field theory that has supersymmetry in it, and then understand eventually how to build the supersymmetric extension of the standard model itself, and then, what the issues are there, So that's where we are heading towards. So hopefully by the end of today, we will have most of the discussion of how to do the MSSM. Okay, so the next thing that we really need to figure out is what are the basic building blocks, the basic representations of supersymmetry that we are going to be using to write down these Lagrangians. Okay, so you can do this algebraically. It's actually very easy, but it's a little abstract, so I won't be doing it. Basically you can use these supercharges as creation and annihilation operators, and you can step through the ladder of the different states within any supersymmetric representation. So if you like, angular momentum or, just harmonic oscillator, you will understand it very easily. But again, I'm just not going to spend half an hour on that. It's fun for those who like to do, who like to play those games. So what I'll just tell you what the most important representations are and what their properties are. And I will be focusing on what is called n equals 1 SUSY. What does n equals 1 mean? You remember yesterday I told you that there are the supercharges. There is the spinor index that tells you that the supercharge is a two-component spinor. And then there's this other index that tells you how many supercharges there are. Yeah, so n equals 1 means that there's only one, that there's no additional index here because there's only one kind of supercharge. Yes. Now, the string theorists would say that n equals 1 actually means 4 supercharges. Yes? So sometimes you will hear that this means 4 supercharges. And that's because these are two components and they are both complex. So you can think of both Q and Q dagger, or you can think of the real and the imaginary part. These are two component complex objects. So the string theorists would say 4 supercharges, and the reason why they rather refer to 4 rather than n equals 1 is because they like to go between different dimensions, and that what is n equals 1 in different dimensions means a different thing. So for them, this is a theory with 4 supercharges. For phenomenologists, this is n equals 1 supersymmetry. That's the basic thing, and that's the one we will be focusing on. Okay? So now, what are the basic building blocks, the basic representations of n equals 1? So those will be called the superfields. So those will be sort of the analogs of a fermion and the boson, but now taking into account that you have to group them together to make sure that they actually form a unit of supersymmetry. Yeah, so these will be called superfields. So again, these will be objects that contain both fermions and bosons at the same time. And there are 2 of these that will be playing the major role for us. One of them is the chiral superfield. And often I will just abbreviate it as a chi-SF. I don't want to write this so many times. So chiral superfield. Okay, and this has one complex scalar and one two-component Weil spinor. Okay, so that's a chiral superfield. And the other basic representation that we will be using to build up a supersymmetric theory is called the vector superfield. And this contains one gauge field and one two-component spinor. Okay. And again, for now, we are talking here about massless fields. And there are many other representations, but these are the only ones that do not involve any fields that have spin greater than 1. Okay, so these are the only representations that do not contain spin that is greater than 1. Okay, and so of course, if you want to use gravity, you want to describe a supersymmetric version of gravity, you will have to go beyond this. Okay, but we are just trying to do normal particle physics, so this is going to be sufficient for us. In fact, again, if you use other representations, you would necessarily get things like spin 3/2, spin 2. So we are trying to avoid those and just have the simplest extension of the standard model. Okay. Now, one other small comment. If you didn't stick to n equals 1 supersymmetry, but if you have more than one supercharge, if n is greater than 1, yeah, so for example, you can hear things like n equals 2, 4, things like that, yes, then it turns out that you will not have any chiral representations. So these are very interesting for formal reasons, but these have no chiral representations. What I mean by that is that here, yes, in the chiral superfield, you have one 2-component Weil spinner. And in any representation of the supersymmetries with more than one supercharge, you will always have sort of, the fermion and the antifermion paired together. Yes? So they will never get a chiral theory for you. And that's, of course, what you need for the for the standard model. Yes? The standard model is a chiral theory. So we know that, in fact, this is what we will want to be essentially using eventually for the matter fields of the standard model. Use for matter of the standard model. So, for example, the electron, the quarks, they will be sitting in these representations, and then the gauge fields, the W and the Z, the photon, they will be living in this representation. Okay, very good. Now, one thing that I would like to note is that you remember I told you yesterday that the number of degrees of freedom that are fermionic and bosonic should be equal within one of these representations, yes? So in particular here, there should be an equal number of degrees of freedom that are fermionic and bosonic, yes? And that's in fact true if you are counting the true propagating degrees of freedom in the theory. Okay, so the counting of the degrees of freedom. Yes, let's say for a chiral superfield, yes. So if you think you have one complex scalar, so that's 2 degrees of freedom, yes. The real and the imaginary part, they are both some, independent, so 2 DOFs, okay. Now how about the complex Weil spinner, the 2-component Weil spinner? Well, naively, the 2-component Weil spinner has actually, 4 degrees of freedom, yes, because it's a 2-component object and it's complex. Yes, so it's 2 times 2. So naively, those are 4 degrees of freedom. Yes, but of course, you know that one 2-component object actually, describes one spin 1/2 actual propagating degree of freedom, yes. So the propagating degrees of freedom here are actually 2. Yes? So you can say that, well, you have to impose the Dirac equation or the analog, the Weil equation on it, yes, to actually get what the propagating degrees of freedom are. Yes, so naively, so the way we would say it is that on shell, meaning the actual true physical matter content is 2 degrees of freedom, which matches that of the propagating degrees of freedom of the bosons. Yes? But off shell, yes, if you don't impose any equations of motion, yes, there would be an imbalance between the fermionic and the bosonic degrees of freedom. So if you want to be able to write a Lagrangian for this chiral superfield that is also valid off shell, yes, you will have to introduce another field, a dummy field, in the sense that it's going to be a bosonic field that contains no true propagating degrees of freedom to make up for this imbalance. So if you want to write the chiral superfield off shell, yes, so if you want to eventually write a Lagrangian, yes, that is relatively easily formulated, then you will have to add another degree of freedom here, yes, which will have 2 degrees of freedom off shell and 0 degrees of freedom on shell. That's why I call it a dummy field. It's sort of something that will have a trivial solution to its equations of motion. Essentially, that field, you know, when you take its equation of motion, you can just express it in terms of the other fields. But without taking the equations of motion, it will make up the difference between the fermionic and bosonic degrees of freedom. So off shell, the way we will formulate the chiral superfield is that there will be a complex scalar. Yes, so this is off shell. There will be 2 degrees of freedom in the complex scalar. On shell, also 2 degrees of freedom. For the fermion, there will be 4 degrees of freedom off shell and 2 on shell. And then there will be this other field. This is usually called F. That's what it's denoted in supersymmetry. So this will be the auxiliary field. Again, it's a dummy field. It's sort of, you know, something that I introduce, you know, just to be able to formulate the theory in the simplest possible way in a Lagrangian, yes, but it doesn't really contain any propagating degrees of freedom. So off shell it will have 2, yes, then 2 plus 2 is 4, and on shell will have 0, so the number of degrees of freedom will be balancing out both on shell and off shell. Okay, so that's the story of the chiral superfield. Now there's a similar story for the vector superfield. So I told you, so the vector superfield I'm going to call VSF. So that's the vector superfield. So I told you that it has 1 gauge field and 1 2-component spinor. So the 2-component spinor, so the 1 Weil spinor, again, off shell has 4 degrees of freedom, just like, you know, no difference here. On shell, 2. Yes. And now I have a gauge boson, 1 gauge boson. Yes. So this gauge boson off shell has 3 degrees of freedom. Yes, but on shell, it only has 2 degrees of freedom. Okay. So now I will need 1 additional dummy scalar field that I have to introduce here. And now this should be a real scalar, yes, because the difference here is just 1. So there will be 1 real scalar. And that will have 1 degree of freedom off shell and 0 degree of freedom on shell. Okay, so this is, again, this is usually denoted psi, or let me call it lambda. Okay, so this is what is usually denoted as the gaugino. Okay, so this field is called the gaugino. And then this is the gauge boson, A mu. Yes, and then this is the auxiliary field. It's a scalar. It's usually called the D field. It's a real scalar. Okay. And just to be sure, okay, so this is, of course, you know, this is the scalar and the fermion. And usually if, you know, the fermion, for example, if it's the electron, then the partner of it is called the scalar electron. So this would be called the fermion. Yeah, so this would be the scalar fermion. Okay. Now, it's going to be slightly different for the Higgs, because for the case of the Higgs, this is the standard model field, yes? And then you introduce a superpartner that is fermionic, so then this would be the Higgs, and then the superpartner of it would be called the Higgsino. Okay, so we'll write down that table very clearly, but just to get oriented of where we are going. Okay, very good. Now, okay, so I have these degrees of freedom, and I would like to tell you now how to write a Lagrangian. How to write a Lagrangian that is, in fact, supersymmetric. Yes? That's the question. Yes? It's not only that I want to write some arbitrary Lagrangian with these fields, but the interactions have to also not break the supersymmetry, yes? Whatever it is. So the best way to do that, and that's sort of one more layer of formalism, but it's really, really useful, I think, if you want to truly understand supersymmetry, this is the part that is the most useful part, is to introduce the notion of superspace. Okay. So basically, I told you that you have to use the superfields, yes, which are containing both the fields that I'm interested in and their superpartners, yes, like for the fermions, you will get the fermions, or you will have gauginos and gauge bosons, yes, and they naturally want to live on a space that is slightly larger than our ordinary space. And if you formulate the theory like that, then you can actually group them together into one simple, slightly more complicated object, which is now truly going to be a superfield, and it's living in superspace. Okay? So how do we understand what superspace is? Yes, well, if you remember yesterday, what we had is, we had this algebra Q alpha, Q bar, beta dot, yes, is equal to something like 2p mu sigma mu alpha beta dot, yes, something like this. So you can see that the supersymmetry transformations are essentially fermionic versions of some form of translation, yes. So this is translation in ordinary space, yes, that's that's momentum in ordinary space. And then the question is, what does the supersymmetry transformation correspond to? And when we introduce this concept of superspace, what we would say is that, well, this corresponds to translation in some other space that is a fermionic version. It's a fermionic space, yes, which is a fermionic coordinate. So we introduce a new coordinate theta here. Theta is the superspace coordinate. Yes, and the supersymmetry transformations would actually do a translation in this superspace direction. So this would be sort of a fermionic version of the ordinary space-time coordinate x, yes? So now we are going to have x mu, and then we will have theta alpha and theta bar alpha dot, yes? This is now going to characterize a point in superspace. Okay, so that's, again, it's a little bit abstract, yes? You will see in a moment why this is useful for you, yes? Because what we are going to be looking for is objects that are now functions of superspace, yes? So a normal field, yes, you would say phi of x, this is a field, yes? Scalar or fermion, depending on, what kind of indices it has. Now we are going to consider objects that are functions of both x and this weird new coordinate, weird new fermionic coordinate, yes? So this theta, so this is a fermionic coordinate. Or if you want, these are, like Grassmann-like numbers, like similar to, the coordinates over which you have to perform the fermionic path integrals, yes? So these are fermionic coordinates, meaning that they anti-commute, yes? So the square of each of these is 0, except again, this is going to be because there is a spinor index here, so the theta is going to have a spinor index, so there are two of these directions, yes? So the square of theta 1, that's 0, yes? But theta 1, theta 2, that's still not 0, yes? So we would usually denote theta squared, yes? That would be something like theta alpha, so that's non-zero, but any higher power of that would be vanishing, yes? Because it's a Grassmannian, it's a fermionic coordinate. Okay, so the fields are going to be functions of the superspace coordinates. And you can then ask the question, what is the effect of a supersymmetric transformation on the superspace? So that's something that, again, oh yeah, I forgot to tack up. I will definitely tack up the homeworks right after, because this is an important one. So this will be the homework for today, is to take one of these superspace coordinates, yes, and act with it with a supersymmetry transformation. Yes. So what do I mean by that? Yes, meaning that, you know, the Q alpha is a generator of supersymmetry transformation. So act with it with some amount of supersymmetry transformation. So the psi is the amount of supersymmetry transformation that you are performing. Yes. And what you want to see is how do these coordinates actually transform under one of the supersymmetry transformations. So you can do both this plus, you know, the complex conjugate and see what is the effect of that on x mu, theta, and theta bar. Yes? And of course, you know, what you expect is that, well, again, you know, this is going to be a shift in the superspace directions, that's indeed what happens. Yes? So this will go over into x mu, theta plus psi, theta bar plus psi bar. But then there will be, because two of these supersymmetry transformations, you know, close into an ordinary translation, there will be another effect here. So this will be plus I theta sigma mu psi bar minus I psi sigma mu theta bar. Okay, so this is what the effect of a supersymmetry transformation on the superspace coordinates is going to be. Okay, so this will be a homework, and you know, many things that you do in supersymmetry really underlies, you know, this formula is what is underlying those results. Okay, very good. So that's the effect of a supersymmetry transformation. So now what I would like to ask is, so how do I incorporate these vector superfields and chiral superfields that I talked to you about in this formulation using superspace? Yes, so now let's take, you know, just what I would call a generic superfield. Okay, so that would be just an object that is a function of x, theta, and theta bar. Yes, so that would be a generic, well, let me not call it F, because F is what let me call it G, a generic superfield. Yes, because F is, you know, reserved for the auxiliary component of the chiral superfield. Okay, so what would this be? Well, again, you know, you start saying, well, any field, I can always do a Taylor series expansion, yes? And the beauty of these theta and theta bars are that, you know, because they are fermionic, you know, their Taylor series is finite, yes? So if I start expanding according to theta and theta bar, very soon, you know, I will run out of, you know, powers of these Grassmannian variables, so there will just be a bunch of finite number of actual ordinary fields contained in this generic superfield. Yes? So there will be here, you know, if I take theta and theta bar equals 0, there will be a scalar field contained in it. Now if I put, you know, the leading order in theta, yes, then there will be a fermionic field, a two-component spinor contained in it. Then the expansion in theta bar, yes, there will be another two-component object, chi bar of x, yes. Then I can take the theta squared, yes. The theta squared is not yet 0 because theta is a two-component spinor, so the theta squared is not yet 0. But it's bosonic, so there would be something like theta squared times another bosonic field here. Yes, then there would be theta bar squared times, n of x, etc. Okay. Oh, so then there is another one. How do you get a gauge field? Yes, that's also contained in this. Plus, there will be a term that is theta, sigma mu, theta bar, and then there will be a gauge field in it. Okay, and then there will be plus theta squared, theta bar, that's another fermion, lambda bar, plus theta bar squared, theta psi, plus theta squared, theta bar squared times d. Yes? So now you understand why superfields are so useful, yes, in the sense that one of these superfields contains a lot of ordinary fields, yes, scalars, fermions, gauge fields, they are all contained in this one single object. Yes. And so eventually, the goal is to use these more abstract superfields, yes, and write the Lagrangian using that formulation. Okay. And again, of course, this ends here, yes, because there's, any higher power in theta, yes, is going to be 0, so the Taylor series is finished at that point. So this is really nice, except I told you that what I'm interested in is the chiral superfield and the vector superfield, and, this is neither of them. It contains, too many things. Yes, so essentially, this generic superfield is sort of a collection of several smaller superfields. And the reason is that actually there are, some conditions. So some of these fields are not going to be mixing with each other under supersymmetry transformations. So the way you would say it is that this is actually like as if you, under rotations, as if you put a spin 1/2 and the spin 1 object together, yes, you can, but you rather want to separate it to the smaller objects that don't mix with each other anyways. Okay, so the way you can do this in the best way is to say that let me take this superfield, this generic superfield, and impose some conditions on it which is actually covariant under SUSY transformations. So if you can impose some conditions on this generic superfield that are SUSY covariant, yes, then whatever field satisfies that constraint is guaranteed to, sort of not be mixing with the other components of the field. So what people usually do is they found these relatively simple conditions for the chiral superfield. The condition is that, and I will explain what this means, d bar of phi is equal to 0. And for the vector superfield, the condition is just that it's a real generic superfield, so that V equals V dagger. Now, what does this symbol mean? So there is a version of the super covariant derivative. The super covariant derivative is d alpha. So that's a derivative with respect to the Grossmanian variable, the one that we defined our superspace. Yes, but there is an additional piece that is coming out from from an ordinary derivative plus, so it has derivative with respect to theta, but also a little bit for derivative with respect to d mu, so the way it's defined is plus I sigma mu alpha alpha dot theta bar alpha dot d mu. Okay, so that's the super covariant derivative, and the d bar, sorry, and the d bar is sort of the analog of this with theta and theta bar exchanged. Okay, so the claim is that this condition, again, because it's formulated in a supersymmetric, using the supersymmetric derivatives, yes, so this is actually covariant, yes, so if you apply, a supersymmetry transformation, the transformed field will also satisfy this condition, yes, so that means that, whatever satisfies this condition is going to be one of the smaller building blocks, so this is what will eventually give rise to the chiral superfield. And the nice thing is that you can very nicely parameterize the solution of this condition, of this chiralness condition, because you can check. So let me write out what the d bar is d bar alpha dot is minus d by d theta bar of alpha dot minus I theta alpha sigma mu alpha alpha dot d mu. And let me erase this, not confuse you. And what you can check is that this d bar alpha dot, this super covariant derivative, acting on this combination x mu plus I theta sigma mu theta bar, that this is 0. Okay? So any combination, any function of this combination of the superspace variables x and theta is automatically going to satisfy this condition. So the solution of this condition that is telling you that you are talking about a chiral superfield will just be an arbitrary function of this variable, of this combined set of variables. So a chiral superfield will be phi of y and theta, yes, where y is this combination here. So you see that theta, so the d bar acting on theta, that's of course also 0 because it only has a derivative with respect to theta bar and the derivative with respect to the space to x. So the d bar acting on theta is 0 and the d bar acting on y, again, that's a non-trivial 0. So any function of these coordinates is going to be solving this condition here. And so you can just say that let me write a chiral superfield as an expansion now in terms of theta. Yeah, so this is going to be now phi of y plus root 2, and this is just some conventional normalization, theta times psi of y plus theta squared times f of y. Okay, so now you see that a chiral superfield in this superspace formulation indeed contains exactly the pieces that we were after. One complex scalar, one two-component fermion, plus another complex scalar, and this will be the one that will have no propagating degrees of freedom. Yes?
So what is the motivation behind
The motivation behind?
this two
Again, so the motivation is that this one here, the generic superfield, yes, it's fine, is a superfield, yes. It has equal degrees of freedom. You can write a supersymmetric theory with it, but clearly has too many things in it. Yeah, so you want to find the smaller building blocks, yes. So you want to impose some conditions on the general superfield, yes, which actually remains covariant, yes. So if I'm able to find some condition that, if I apply this to the supersymmetrically transformed one, it remains the same, yes, then clearly this thing is not going to be mixing with any of the other components, yes. So whatever solves this is guaranteed for you to be sort of an irreducible representation. So the way we would say it is this is a reducible representation of supersymmetry. And if you find these conditions that that are covariant under supersymmetry transformations, those will give you sort of smaller objects, yes. Now, is it irreducible? Yes. I'm not sure you can say that right away, but I told you what the irreducibles are, and this one indeed matches up exactly the one that we were after, which is the chiral superfield. And then this one is going to match up exactly the vector superfield condition. Okay, so again, there's of course a little bit more. I'm trying to tell you a lot in in little time. So to truly understand this, I would really recommend that you try to go through some of this algebra, and it's not very hard once you understand what it means. Yes, but to get really the hang of it, you probably have to practice it a little bit. Okay. So, yes. Yeah, of course.
So in some sense, doing this is like taking a SUSY transformation, right, with where you basically choose xi bar to be minus theta bar, which puts the third coordinate to 0. It's like choosing a gauge, no? It's like you're putting the theta bar to 0, just using the formula you have there.
I guess that's probably, you can probably say it like that, yes.
Because it has exactly, it shifts x to your y,
right,
and it sets theta bar to 0.
Right. Yeah, I guess that's true, yes. Just thinking about the signs. Yeah,
so
probably.
C equals 0, and xi bar equals theta bar.
Right.
Or minus theta
bar. You
Yeah.
can probably formulate it like that. I haven't seen it said like that, but it sounds about right, yes. Right. Yeah. Right. Yeah, it's probably like choosing a gauge in that sense, yes. Okay, very good. So now we have the expression for the chiral superfield, and again, it is just, essentially like an object that only depends on theta, but it's not quite only depends on theta, yes, because there's a little bit of theta bar dependence here in the y coordinate, yes, where y is this combination there, yes, but essentially it only depends on one of the superspace coordinates. Okay, and so now what you can do is you have your chiral superfield, yes, so you can ask how does, once you have this, yes, you can go ahead and do a full supersymmetry transformation on your chiral superfield. Yes, so now you really know how these various fields are going to be transforming into each other under supersymmetry. Yes, until now I haven't really told you that. Yes, but once I have this formulation, it's really easy to derive that. If you don't use it this way, there will be really pages and pages of algebra, and this is the thing that, the Vess and Zumino found back in the early 70s, how to do the supersymmetry transformations of these fields into each other, to maintain supersymmetry. But now, with our understanding, it's very easy, yes, because all you do is you just apply e to the I epsilon q plus epsilon bar q bar on this field, yes, on this phi field, on the full chiral superfield. We know how, what the effect is going to be. So you just expand now this shifted this shifted chiral superfield in terms of the in terms of the transformed coordinates, and then you'll find immediately how these things transform into each other. So for example, the scalar is going to transform, not too surprisingly, yes, under supersymmetry transformations into the fermion. Yes, so it's going to be √2 epsilon times psi. Yes, and this makes sense. Yes, this is the transformation of a scalar. Yes, epsilon is the supersymmetry transformation parameter. So this is fermionic. Yes, and then that's contracted with a fermion. So this is a boson here. But still, it's telling you that a boson transformed into the fermion under supersymmetry transformations. Now, you can check what the transformation of the fermion is. So now this is going to have the derivative of the scalar, d mu phi, and then there's an epsilon bar, and sigma mu and root 2I plus root 2 epsilon times F. And then the transformation of the auxiliary field, the F, is going to be root 2I epsilon bar sigma bar mu d mu of psi. Okay? So these are the SUSY transformations of the different components of the chiral superfields. And historically, this is how, in fact, supersymmetry started even worse than this, yes, because people didn't know initially that you have to have this auxiliary field, and if you remove the auxiliary field from the theory, then of course the transformation is much more complicated because it will make it nonlinear. Yes. But anyway, so this is how supersymmetry essentially started. Yes, people wrote down these weird transformation rules, and it was hard to understand where it is coming from and what the origin is. But using this sort of roundabout way with superspace and superfields, it's actually relatively easy. I mean, of course, I haven't completely shown you that this is the result, but I outlined you, how you can probably get it in less than a page, yes, rather than doing, several pages of algebra. Now, one thing I would like to emphasize is that actually the transformation of the highest component, so we call this the highest component of the chiral superfield, of the auxiliary field, yes, goes into a total derivative. Okay, so the transformation of F is into a total derivative. Okay, so what this means is that if I take, a chiral superfield, yes, and I somehow pick out its highest component, yes, that will be something that is automatically invariant under supersymmetry. Yes, that will be a candidate for a Lagrangian term. Yes, because it picks up a total derivative. So if I integrate it over d4x, yes, then that piece is actually going to be just a boundary term, again, assuming that the fields fall off as usual sufficiently fast, then this will be a candidate for a Lagrangian in the candidate for a Lagrangian term. Yes, because again, it's a total derivative, so if I take the highest component, if I take an arbitrary function of chiral superfields, so for example, take a, something that is linear, cubic, quadratic, whatever, any power of chiral superfields, you can check that any product of a chiral superfield remains a chiral superfield. It's because, if I have phi is equal to, the d bar of phi is equal to 0, if I take phi squared, you can show that, of course, any product of it is going to remain a chiral superfield. So I can take an arbitrary function of the chiral superfields, yes, and I can take the F component of this. Yes, the way it is usually written, actually, you introduce the integration over the superspace variables, and you say that this is actually equal to the integral of d2 theta of w of phi. Okay. So this term, again, is going to be something that is invariant, that is a total derivative under supersymmetry transformation. So if I now take an integral d4x of this, yes, if I take an integral of d4x of that arbitrary expression, integral d4x d2 theta of an arbitrary function of these chiral superfields, yes, this is something that is a candidate for the action. Yes, because once I do the integral over space-time, because it was a total derivative, this is supersymmetrically invariant. So this is a SUSY invariant, yes, and looks like a Lagrangian, yes, looks like an action. Now, one thing that's important is that, of course, this W should only be a function of the chiral superfields, yes? It should not be a function of the complex conjugates of the chiral superfields. So it should not contain phi dagger. Should not contain a complex conjugation, because if you take the d bar on phi dagger, that's not 0. So that's not a chiral superfield. It's going to be an anti-chiral superfield. So of course you can add, the complex conjugate of that, yes. So the complex conjugate would contain a term of the form d4x and d2 theta bar of w bar of phi dagger, yes. So that's of course there, yes. But that's sort of, it's just the complex conjugate of it. What you cannot have is something like d2 theta w of phi dagger. Yes, that's not allowed. Yes, so that's not going to be supersymmetrically invariant. Okay, so the way we usually say it is, this is what the sort of more formal people like to say, is that W is a holomorphic function of the chiral superfields. So if you go to SUSY-related talks, you will hear, holomorphy here and there. This is where it comes in. Yes, that this function, which is called a superpotential. Why is it superpotential? Yes, because it sort of plays the role like the ordinary potential in ordinary non-supersymmetric quantum field theories, but it's just a holomorphic function of the chiral superfields. Okay, very good. Now, so this is one way of getting pieces in the action. Yes. Now, there's another way, yes, that you can try to ask, okay, so if I take arbitrary powers of the chiral superfields, that's how I get some term. What happens if I take phi dagger phi? Okay, so now this is not a chiral superfield anymore. This is not chiral, meaning there is no difference. I mean, in phi, there's a distinct role of theta versus theta bar. In this one, in phi dagger phi, clearly they are going to be on the same footing. So you can actually go ahead and calculate what is the highest component of this combination. The highest component of this combination will now contain a piece that is as high as it can be, yes, like in our expansion. The highest possible term in these theta coordinates is theta squared, theta bar squared. Yes? So it will contain that piece. And actually what it is going to be is it's going to be FF dagger plus 1/4 phi star box phi plus 1/4, I don't know why I wrote it in this stupid form, box phi star phi minus 1/2 d mu phi star d mu phi plus I over 2 d mu psi bar sigma bar mu psi minus I over 2 psi bar sigma bar mu d mu psi. And what you recognize is that this, so the highest component of this non-chiral superfield, yes, of this phi dagger phi, is actually exactly what you would call the kinetic terms, the ordinary kinetic terms of a scalar field, two-component Welch spinor, and very nicely the sort of kinetic terms of my auxiliary field, this dummy field that I introduced only to make up the difference between the fermionic and bosonic degrees of freedom, doesn't have any derivatives, yes? So if I call this the kinetic term of F, yes, then it's in fact going to be a non-propagating degree of freedom, because its equation of motion is not going to contain any derivatives. Yes, when I take its equation of motion, I will just be able to analytically solve F in terms of the other fields, in terms of phi and psi. And essentially, I can integrate it out. I can solve for it. Yeah? So that's what it means, that it doesn't have, doesn't contain a propagating degree of freedom. Okay, so this is telling us now how to write the Lagrangian for these chiral superfields. So this is like one of the basic steps. So the Lagrangian for a chiral superfield will contain the kinetic terms. So So that's a d4 theta phi dagger phi. Yes, and then there will be a d2 theta of w of phi plus Hermitian conjugate. Okay. Now, so again, this is called the superpotential. Sometimes, people want to write more general expressions, and I'm not going to be use it. But sometimes, people generalize this to have some arbitrary function, arbitrary real function of phi dagger and phi, and then this will be called the Kähler potential. Okay, we won't be using it too much, but it's good to at least hear the nomenclature. If you are learning about supersymmetry, that instead of this kinetic term, usually you can write these higher order terms. I mean, you probably want this to start with phi dagger phi, but there could be higher terms. Which yes.
Could you explain a bit more how the kinetic terms come out of these?
So again, so this is you just have to do this product, yes. So I told you how to write out phi, and now you're going to write out phi dagger also. Now, where are the derivatives? Yes, where are it's in the fact that it's a y. Yes, that this is a function of y. It's not quite a function of x. Yes, so phi of y, yes, is equal to phi of x. Yes, plus, yes, there will be this I theta sigma mu theta bar times d mu of y, of phi of x. Yes. And so when you take the highest component, you can see now theta theta bar, essentially you square that, yes, you are going to get d mu phi star type terms showing up. Okay, so that's where it is hiding, yes. In this formula you say, well, there are no derivatives here, how do I get a kinetic term, yes? But again, that's what I said. It is important that this is a function of y, is not a function of x, yes, where the y is this combination of, so it's not quite independent of theta bar. Yes, it's okay. Any other question? All right, very good. So now this is the Lagrangian, and now the other important thing is that, as I said, the kinetic term for F is very simple. Yes, so you can actually just take the equation of motion. So you can just take, the equation of motion for F. Yeah, so you can just take, the dl by df. Yes, and there are no derivatives there, and you can solve that. Yes, and then from there you can solve F in terms of the derivatives and every other the phi and the psi. And what you're going to get is a very simple theory. Yes? So in terms of if I integrate out F, yes, then the Lagrangian that I'm going to get is just d mu phi I star, d mu phi I, plus I psi I bar, sigma bar mu, d mu psi I, and then minus d2w, d phi I, d phi j, psi I, psi j, minus sum over I, dw by d phi I, absolute value squared. So this will be the Lagrangian of this chiral superfields, or here I added already several chiral superfields with some arbitrary superpotential. Yes? So you see it's very simple. Yes, just has the normal kinetic terms for the scalars, normal kinetic terms for the fermions, has some Yukawa couplings, yes, because this is the derivative of this function, yes, but you still have to keep this as a function of those of the scalar components of the superfield, and here this is just the scalar potential. Okay, so first of all, the most important thing you should notice is, of course, supersymmetric theories are ordinary field theories. Yes, there's nothing, in fact, they are simpler than, they are very special ordinary field theories. Yes, even though we write it in this fancy way with d2 theta, d4 theta, etc. But, they are just you know, theory of interacting scalars and fermions. Yeah, so there's nothing, you know, mysterious about them. What is special about them is that, of course, again, the number of fermions and bosons have to match. And, yes, the Yukawa interactions and the pieces in the scalar potential, so for example, quartic self-interactions, are related to each other. Yes, they come from the same function. Yes. The Yukawa coupling is the second derivative of the superpotential function. Yes. And the pieces in the potential, like quartics, yes, they are squares of the first derivatives. Okay, they are related to each other. That's what makes it supersymmetric. The fact that there's this non-trivial relation between, you know, two, you know, generically you can say, oh, I have some bunch of fermions and scalars and I write Yukawas and quartic self-interactions. You can do it, but generically it's not going to be supersymmetric. This is the condition, the fact that you have to have a particular relation between the Yukawa couplings and the scalar potential is what makes it supersymmetric. Yes? So this is now an interacting theory that has this additional, you know, weird symmetry that, you know, you would not have necessarily recognized ahead of time. Okay, so that's the story of how to write the Lagrangian just for the chiral superfield. So this used to be called at some point, I guess it's still called the West-Zumino model, yes. So this is like the simplest version of an interacting supersymmetric field theory, yes.
Can you just repeat
Why
why is D4 theta?
is D4 theta, yes. So D4 theta is actually, what it stands for is D2 theta bar. So that's an abbreviation for that, okay. I don't know, this is how, so of course, you know, only, you know, there are no force power of just theta, yes. So people, you know, when they say D4 theta, they mean D2 theta bar. That's the meaning of this integral. And again, you know, what it's trying to do is it's trying to pick out this highest component here. Yes. So it's like doing the Grassmannian integral, yes, over theta. Yes. So really, the way you should understand this equation is that you start writing out phi dagger phi, and there will be many components, and then there will be a term that is of the order of theta squared, theta bar squared, and this is what's written here. Yes. And, you know, what I'm saying is that, well, that's the piece that I see is looking like the kinetic terms for an ordinary Lagrangian. So let me pick out this term from, you know, the product of phi dagger phi. So one way to say it is I'm just picking it out, but, you know, the rules of Grassmannian integration you're probably familiar with just from fermionic path integrals, yes? So things like, you know, d theta is equal to 1, yes, and integral d theta is equal to 0, yes. So essentially, I'm just applying those rules and saying that integration is the same as differentiation and is the same as just literally picking out the piece that is the coefficient of this term, okay? All right, very good. So that's the story of the chiral superfields. Now you have to repeat this for the vector superfields, and I'm just going to do this relatively quickly and schematically because, you know, there's no point in, you know, I mean, you understand the logic, yes? So for the vector superfields, well, so first of all, how do I make it a gauge theory? So I want to make it a gauge theory because, well, the standard model is a gauge theory, yes? So that means that these chiral superfields will have to pick up some charge. Let's do it first just for a U1 gauge theory. So let's say that phi carries a U1 charge. Like if I want to write down the Lagrangian for QED, for example, carries a U1 charge. It means that under gauge transformations, yes, it is going to pick up a phase, e to the minus I lambda, where this lambda better be, so this is the gauge transformation parameter, yes, this is the phase transformation of ordinary U1 gauge theories, yes, this better be itself a chiral superfield, yes, because otherwise, you know, chiral superfield doesn't remain a chiral superfield under gauge transformations. Okay, so now what? But I know that I will have to have a phi dagger phi type term in my Lagrangian, yes, because you know that's how I make the kinetic terms out of it. Now, how does this transform? Yes, well, this is going to pick up an e to the minus I times lambda minus lambda dagger, yes, phi dagger phi. Yes, that's what it's going to pick up. And now what I want is that this kinetic term actually becomes invariant, yes, under gauge transformation. So now I'm trying to introduce the gauge field here. Yes, well, so the gauge field will have to suck up exactly this additional phase, yes, that comes in to the transformation of the kinetic terms of the chiral superfields under gauge transformation. So the way I should do this is to introduce here a field V, a chiral superfield that picks up exactly this transformation plus I times lambda minus lambda dagger. Yes, so it's going to pick up exactly the opposite of this phase that is showing up here, and then the gauge covariant way of writing the kinetic terms for the chiral superfields, yes, is going to be like this, yes, because the phi dagger phi, again, is picking up this phase, and then the V, this vector superfield, the one that is going to contain my gauge fields, is exactly going to be canceling this phase. So this is basically the supersymmetric generalization of how to write the, you know, the gauge covariant Lagrangian for the theory. Okay, very good. And so what you need to do is you need to also write out the expression for the vector superfield in terms of its components. So you want to solve V equals V dagger. Now it turns out that this one has lots of components. The solution of it has lots of components, but many of them are just gauge artifacts. Many can be gauged away. So we usually just write out, at least for our purpose, we just write out, you know, the gauged fixed version of this vector superfield. It's called the Vezumino gauge. And in that particular Vezumino gauge, the vector superfield is going to look like this. So minus theta sigma mu theta bar V mu plus I theta squared theta bar lambda minus I theta bar squared theta lambda plus 1/2 theta squared theta bar squared d. Okay, so this is the gauge field. Usual, you know, like the photon or the W and the Z when you generalize it to non-abelian gauge theories. Lambda, so this is a fermion. Yes, it has a theta squared theta bar. So there is an odd number of Grassmannian superspace coordinates. So lambda is a fermion. So that's called the gaugino. Yes, it shows up in two places. Yes, because this has to be a real, you know, V is equal to V dagger. So this actually has to be the same field there. And then the D is the auxiliary field, the auxiliary D component. Okay, and so that's one way to write the the vector superfield. Now, and this contains V mu. There's another form to write the vector superfield which will directly contain the field strengths, and sometimes you will see that. I'm not going to use it very much, but I'll just tell you quickly to be sure if you ever see that notation, you understand what we are talking about. So there's another equivalent formulation where you write W alpha is -1/4 d bar d alpha on V. Okay, so you see W has the same content as V. Yes, so you can use them interchangeably. Why is this sometimes more useful? Well, because this one actually is a chiral superfield. Yes, because you see, I acted already with 2 d bars on something. So if I act with a third d bar, this is going to be vanishing. Okay, so it's actually a chiral superfield that has the same matter content as the vector superfield, and often, it's slightly more useful. So the W alpha in terms of the expansion, so this is now, you see, it has a spinor index and it has 3 superderivatives, so it's actually now fermionic, so its lowest component is going to be the gaugino. Lambda alpha is the gaugino as a function, again, of this y coordinate. The y coordinate, the combination of x and the theta bar like we had before. And then, there will be a piece that is proportional to theta times d minus, there's some piece here with sigma bar f mu nu. This is sigma mu, sigma bar f mu nu, something like, I'm just writing it schematically. And then there's a theta squared times sigma mu, d mu, lambda alpha. Something like this, okay? I won't use it very much. I just wanted to make sure that you understand that there is a chiral superfield version of the vector superfield, and that starts out with the gaugino, and it contains now just the field strength tensor, okay? And now the nice thing about this is that if you want to write sort of the analog formulation of the kinetic terms for the gauge fields, yes, clearly this is going to be the better way because this already contains f mu nu. Yes, so the square of this actually, so it's like a chiral superfield. Yes, I can take the square of it, that will contain 2 f mu nus, and if I take the highest component of that, the theta squared component of that is going to be a good term for the Lagrangian. So if I take W alpha theta squared, which is again d2 theta W alpha, yes, this is going to contain the kinetic term for f, so it's going to contain the f mu nu squared. It will contain the usual kinetic term for the gauginos, the lambda bar, sigma bar, d mu lambda, and the d squared term. Again, for the auxiliary field, there will be no derivative showing up, just a mass term. So again, you can integrate it out. So this tells you now how to write the Lagrangian for a gauge theory. So for example, let's do first a baby version. Yes, let's do QED. Yes, how to write the Lagrangian for QED. Yes, so first of all, let me just remind you again. So the SUSY Lagrangian, L SUSY, is, so there's the kinetic terms for the matter fields. Yes, so I have different matter fields, phi I put them into chiral superfields, and it will have all kinds of gauge interactions. So e to the GV is what is needed to make this gauge invariant. Yes, and then I will have the superpotential term, sorry, the kinetic terms for the gauge fields themselves. Yes, so W alpha. Sometimes we put this 1/4 here, plus Hermitian conjugate. And then the superpotential term, integral d2 theta W of phi plus Hermitian conjugate. Okay? Yes, go ahead.
Why always we are taking the highest component of the expression?
So again, for these guys, I explained to you that that's a total derivative. Yes, so that will be a good candidate for an action. Yes, and in fact, you can show that that's always true. So the highest derivatives, the highest components of these superfields, they have no other choice. Yes, because there's no new field that you can bring in. It has to be related to to the derivatives of the fields that are already present at the lower order. Okay? So these will always be total derivatives. Okay?
It would be like we are going to higher orders in the case of superfields, but then we are going back to like standard model or something like this.
Well, sorry. So of course, eventually we want to write the Lagrangian for the supersymmetric version of the standard model, yes. But the question is how to write it in a way that the interactions maintain supersymmetry. Yes. So the reason why this picking out this highest order term is the useful thing is because that's what will give you something that is invariant under supersymmetry. Okay. So this one makes it invariant under SUSY. Again, the logic was that I did a supersymmetry transformation of the various fields, and what I found is that the highest component goes into a total derivative. And that's always true, yes? So if you pick out highest components, either of a generic superfield or of a chiral superfield, it always has to be on its own, sort of going into a total derivative, which means that the d4x of that, yes, is invariant, is supersymmetrically invariant. So those are always the candidates for action. Now, of course, eventually you will also want to make sure that it's gauge invariant and that it's Lorentz invariant. Yeah, that it's the highest component is making sure that it's supersymmetrically invariant. Okay. Of course, the charges under gauge symmetries will still have to add up to 0, etc. Yes, that's on top of it. But this is how you write supersymmetric Lagrangians. Okay. Yes.
So I have a slightly stupid question.
No questions are stupid. So.
So the one that is with W alpha.
Yes.
On the right hand side, some of the alpha indices are missing, right?
Yeah. So I didn't. I was pretty. Yeah. So on the right hand side, I can be more. I tried to. Okay, so this is a theta, beta, delta, alpha, beta. I just, didn't want to waste the time, but, I don't want to give the impression that there is something mysterious here, yes. And now they match, and then this one has here sigma mu alpha, alpha dot, and then, okay, lambda bar alpha dot.
Yeah, okay. Because I didn't know.
Yeah. No, I was just writing it schematically. But they match, yes. I was just lazy. Just try to cheat a little bit, yes.
But then there are no other terms that do not vanish because they contain total derivatives that maybe could.
There are no other supersymmetrically invariant terms, yes. Right. Okay, very good. So let's try to, again, we'll do this example for QED, and then we'll go to the standard model. Okay, so how would I write QED? Okay, so this is, again, it's just to get the first idea. Yes, so what would be a supersymmetric version of QED? So quantum electrodynamics, yes. Well, so I would have so QED is a theory is a U1 gauge theory, yes, and it's the U1 gauge theory of an electron, yes. But an electron, we usually think of it as a Dirac fermion, yes. But in the case of supersymmetry, our chiral superfields contain, only two component objects, yes. So the way we usually do this in supersymmetry is to assign both the electron to a chiral superfield. So this would be the electron chiral superfield. And then, I need two more components, yes? So I will call that the positron, the phi plus. So that would be the positron chiral superfield. Yeah, so these are both chiral superfields, but have opposite charges under ENM, under the U1 gauge theory. Okay, so that's essentially it, yes, because once I understand, so these will be my matter fields, and then on top of it, I will have the V, yes, so this is the photon vector superfield. Yes, and once I have it, I can just go ahead and write down my, just turn the crank because, I worked hard to tell you, what the way is to write a Lagrangian for theory like this that is supersymmetrically invariant. Okay, and so this is equal now, again, we will have the 1/4 W alpha, yes, so that's the kinetic term for the photon and the photino. So this has the photon and the photino as propagating degrees of freedom in it. So I will have this plus Hermitian conjugate, and then, sorry, this is d2 theta. Yes, then I will have d4 theta, the kinetic terms for the positron and the electron. Yes, so I will have here phi plus dagger. The plus means that this is the positron, and this plus here means that it's the dagger is the complex conjugate of the of that superfield. Yes, e to the e times v. E is the electric charge. Yes, and v is the photon vector superfield. Yes, plus phi minus dagger, e to the minus e times v, yes, because this is now a negatively charged object, times phi minus. So that's the kinetic term for the electron and the positron. And then I want to add the mass term for them. Yes. So the mass term will be written in terms of the superpotential. Yes. So that's just m times phi plus phi minus. Okay, plus Hermitian conjugate. Okay, so that's it. That's the Lagrangian. And now if you want to write it out, yes, write it out in terms of fields, just once. It's probably a useful thing to understand. So the Lagrangian for supersymmetric version of QED is, well, so there will be the kinetic term for the gauge fields. So that's 1/2 d squared minus 1/4 f mu nu f mu nu. Yes, minus I lambda sigma mu d mu lambda bar. Okay, totally standard. Yes, again, it looks mysterious if I write it like this, but in terms of the components, it's just a normal kinetic term for a photon and the photino, which is the fermionic partner of the photon, and the mass for the auxiliary field. Now the kinetic term for the matter fields, F plus dagger F plus F minus dagger F minus plus d mu phi plus absolute value squared plus d mu phi minus absolute value squared plus I times psi dagger d mu sigma bar mu psi plus I psi minus bar d mu sigma bar mu psi minus. And now here come the interesting important terms. Yes, the term that is forced on you by supersymmetry, which wouldn't necessarily, you would not have necessarily guessed, minus I e over root 2 times phi plus psi plus bar lambda bar minus psi minus bar lambda bar plus Hermitian conjugate. And then there are these two terms, d times phi plus absolute value squared minus phi minus absolute value squared, and plus m times phi plus f minus plus phi minus f plus minus psi plus psi minus plus Hermitian conjugate. Okay, so let's try to understand what is it that I wrote down. Yes, we understand this. It's just the kinetic terms for the gauge fields. This is the the covariant kinetic terms for the positron and the electron, yes? So that's automatically, so the fact that I put in here the e to the EV, yes, that will automatically take care of the fact that the kinetic terms have to be covariant, yes? So you don't have to work very hard for that. So that comes out. Same for the kinetic terms for, so these are the, so this is the selectron, and this is the positron, yes? So this is the scalar version, the scalar superpartner of the electron, the scalar superpartner of the positron. These are the gauge covariant terms for the electron and the positron. And now this is something that you would not have necessarily guessed. Yes? So this is now a Yukawa interaction between the positron, the scalar positron, and the photino. And its strength is governed by the gauge interactions. It's a Yukawa coupling, but its strength is governed by the gauge interactions. Okay, so that's the only way to make this theory supersymmetric. It's got to be there, and it's not a free parameter. It has the gauge coupling in it. Okay, and then these guys here, yes, so this is a coupling to the D. Now if I get rid of the D, if I take the equation of motion with respect to the D, I'm going to get an equation, yes. Let's say I take the equation of motion with respect to the D, I get an equation that D is equal to E over 2 times phi plus squared minus phi minus squared. Yes? So now if I substitute it back, yes, this is going to be a quartic scalar self-interaction, yes, between the scalar electron and the scalar positron. Okay, so that's necessarily there. Is also governed by the gauge interactions. Okay, if I integrate out the F's for the electron and the positron, yes, then I'm going to just get scalar masses, yes, the masses for the selectron and the positron, yes, that are matching up the masses, the actual mass of the Dirac electron, the 4-component Dirac electron. This is a Dirac mass, yes, of the electron. Okay, so that's the story of QED. And now we can do the standard model. Yes, so now that we have come this far, we can actually do the standard model. So let's first try to remind ourselves what the matter content of the standard model is. Yes, and I'm going to write it in a form that is most useful for the supersymmetric extension. Okay, so what is the matter content of the standard model? Yeah, so the standard model is now an SU3 cross SU2 cross U1 gauge group. Yes. And I'm going to write everything in terms of chiral superfields. Okay, so I will not add any anti-chiral superfield. So that means that I will write everything as left-handed fermions. Yes. So that means that, you know, the right-handed electron, yes, I will take it as the complex conjugate of the, so instead of taking the right-handed electron, I will take the complex conjugate of it. So I will write a positron just like I did over there for QED, such that I can formulate everything in terms of chiral superfields. Okay, so what's the right formulation then? So you have the Lepton, the doublet for the standard model, and then you have the right-handed electron, yes, but instead of that, I will take the left-handed positron. And the way I'm going to denote it is with an E bar. Okay, so this is a chiral superfield, left-handed, yes, but we'll have the opposite charge. Yes, we'll have the opposite charge as the electron. Now I will have here the quark doublet, and then for the right-handed quark doublets, again, I'm going to take the complex conjugates of those. Okay, and then I'm going to have here the Higgs fields, H up and H down, and I will explain in a moment why I need two of those. Okay, so this is the table of representations. Yeah, so the leptons don't transform under QCD. The quarks are triplets. Now the right-handed quarks were triplets, but now I'm taking the complex conjugates of the right-handed quarks. Yeah, so these will be anti-triplets. So these will be 3 bars, and then the Higgs doesn't transform. Okay, and These are doublets under SU2 left. So this is the usual SU2 left hypercharge, singlet, doublet, singlet, singlet. These will be doublets, the Higgses. Yes, and then under hypercharge, yes, these are the usual standard model hypercharge assignments. -1/2, +1, 1/6. Again, this is +1 because I took the complex conjugate field. Yes, 1/6, and then I have the opposite, -2/3, 1/3, and then I have here 1/2, -1/2. Okay, so the one thing that I had to change, the only thing I had to change with respect to the standard model is that I had to introduce 2 Higgs doublets. There are 2 reasons why I have to introduce 2 Higgs doublets. One is if the Higgs is a scalar and I put it into a chiral superfield, yeah, so it will have a fermionic partner. So if I have only a single doublet fermionic partner that I added on, then I took the standard model fermionic content, added a single doublet, yes, that's going to be anomalous. So I have to have an even number of doublets. So that's one reason. The other reason is that if you remember, the Yukawa couplings in the standard model contain a complex conjugation. Yes? But I told you complex conjugation is a no-no in supersymmetry. Yes? So instead, what I have to do is I have to introduce a second Higgs doublet with the opposite quantum numbers, which is essentially, playing the role of the complex conjugate of the standard model Higgs. Okay, so very good. So this is the matter content. Now let me also write down here the Baryon and Lepton number quantum numbers. Yes, so these are leptons, so they don't carry baryon number 1 - 1. These are baryons, so they carry 1/3, -1/3, -1/3, and then 0, 0, and then these are all zeros here. Okay, very good. So I can start writing down the superpotential terms, yes, which are going to be needed because we will need to generate, yes, I know. So these are the superpotentials of the standard model, lambda up ij, qi, h up u bar j. Yeah, so this would be, the usual Yukawa couplings that give rise to the up quark masses, but now written in terms of chiral superfields. Okay, so they do contain the usual Yukawa couplings, but they will contain other stuff, yes, because these now all contain both scalars and fermions, and so it will contain other stuff. Then I have the lambda d, ij, qi, hd, d bar, j, and then lambda e, ij, li, hd, e bar, j, plus mu h up, h down. Okay? So these are good. So these are needed. Now, before I go, I just want to say one more very important comment, that these match up all the terms, these contain all the terms that are present in the standard model. Now, if you look at the charge table that I have written down here, just based on the gauge symmetries, actually in the supersymmetric extension, I can write down more terms. Okay? There are additional terms that are allowed for the superpotential. In the standard model, yes, what you do is you just take everything that the gauge symmetry allows, you write it down, and you're done. In supersymmetry, the situation is not that good. So there are these bad superpotential terms. Let me call this alpha 1, qi, lj, d bar k, and then it has some coefficients, and then alpha 2, ijk, li, lj, e bar k, plus alpha 3, li, h up, plus alpha 4, ijk, d bar I, d bar j, u bar k. Okay? So these terms are allowed by the gauge symmetries. Okay? However, you can see that these actually violate Lepton number and Baryon number. Yes? So these are delta L is equal to 1, delta L is equal to 1, delta L is equal to 1, and this one violates Baryon number, delta B is equal to 1. So in this sense, supersymmetry is very different from the standard model. If you take the standard model and you write down the most general Lagrangian that you can, that at the renormalizable level, Baryon and Lepton number are automatically symmetries. We call them accidental symmetries of the theory. Yes? That's not true for supersymmetry. If I wrote down the most general Lagrangian, at this point I'll be dead. Yes? If I allowed these coefficients to be, sizable, this theory is totally excluded. Okay? So you have to do something. You have to add an additional layer, something that will forbid these operators. So I think I'm going to stop here, and I'll start with that tomorrow. So that will lead us to the concept of R parity and many of the important consequences for supersymmetry. And then we'll do supersymmetry breaking, and I guess a little bit of flavor violation tomorrow, and that will probably, I will try to wrap up everything about SUSY tomorrow, because then we'll need to move on to composite Higgs models. All right, let's stop here for questions. Yes?
So when you wrote down the table with the degrees of freedom, I couldn't help but notice that if you had a massive boson, you would run into trouble because you would have too many on-shell degrees of freedom. Massive gauge boson. Yes. Well, massive boson. Maybe not. You don't call it a gauge anymore. Maybe you give a Stuckelberg mass or something like that.
Right. But the nice thing is that there's a supersymmetric version of the Higgs mechanism. So you can actually show that the way the Higgs mechanism is going to work is that you take a massless vector superfield, yes, with the table that I had, and then you put the Higgs into a chiral superfield, yes, and now that one has both scalar and fermionic degrees of freedom, yes. So actually, the vector superfield is going to eat a whole chiral superfield, and it will now contain, it will rearrange themselves. Of course, the massive gauge bosons are now going to have 3 degrees of freedom, yes, but it's going to be partly coming from the bosonic degree of freedom of the chiral superfield, which will then come along with its own fermionic degree of freedom. Okay, so you can show that that is perfectly sensible, and the number of degrees of freedom are actually going to be matching. So there's a separate matching for the degrees of freedom for the massive vector superfields. Yes. So now, of course, they will have 3 gauge bosons, and then they are going to have one real scalar, yes, and two gauginos essentially. The original gaugino and the one that was eaten by the. So it's going to be 4 plus 4 now.
But there is no way I can describe, let alone gauge theory, if I want to describe something that it's a massive vector, without caring about, maybe the fact that it breaks unitary at some point. Maybe I want to describe something weird. I can't do it in. I can't put it into the same SUSY superfield.
Sure. So you can you can define a massive vector superfield. Yes, it's going to now have again, a massive gauge boson, 3 degrees of freedom, a real scalar, 1 degree of freedom, and 2. You can say it's a Dirac fermion, yes, which will now have 4 degrees of freedom. Yes.
Okay. Thanks.
I just wanted to know if you have a bibliography that you would recommend just at SUSY.
I'm sorry, what?
A bibliography, a book.
Yeah. So,
a paper.
Well, actually, the author is sitting right here, yes, John Turning. It's called Modern Supersymmetry. And he's here this week, so you can back him. He will be happy. He's part of the workshop that is going on. So that's one. And so that has the MSSM very nicely in it. Now, I really like the book by Wessenberger. So that's really nice for understanding superspace and what the superfields are, how to transform. I think that's a really good one. And then there's Steve Martin's review. That's on the archive. And I forgot what the title is, but you look for Steve Martin and more than 500 citations or more than 1,000 citations, and then you'll find it. So I would say those are, so this is the most phenomenological, this is the most formal, and John's is sort of in between. So Susie Primer, yes, Susie Primer, exactly, that's what it is. Susie Primer is a classic. And I think he initially wrote it in 4 components, and then I think he... Yeah, so he wrote several versions, so you can do it with superfields, with with components. So yes, yeah, he keeps updating. It's also beautiful. So I would say these are probably. I mean, there's also the infamous book that's supposed to appear by Howie Haber and Herbie Dreiner. It was supposed to appear. Probably now it's really in the publisher's hands. So. Maybe it's a little late, yes, but yes, well, there was one more. Yes, go ahead.
Yeah, I was wondering for string theory, if you have n equals 4,
yes,
and you cannot have chiral superfield, how do you reproduce standard model?
So you have to have branes. So basically, there is a way of getting. So there's a way of getting chiral theories out of. These non-chiral higher dimensional theories, and you have to impose boundary conditions. Essentially, there are defects, and the defects of the theory don't have to be chiral. So it's the presence of branes.
Thank you.
Orbifolds, orbifold boundary conditions, essentially.
You have said about the Higgs that we have to use the up and down components. If I want to introduce the neutrino fields, I would have to use just like that to introduce the neutrino, the anti-neutrino field?
So for the neutrino, so the neutrino is contained here, yes?
Oh, okay.
So neutrino is contained here. You could introduce a right-handed neutrino if you want, yes? There's nothing wrong with it, but you're not forced to, yes? The thing about the Higgs is that that's the one where you complete a scalar with fermionic partners, yes? Mm-hmm. All of these here, you're adding scalars to existing fermions. So you don't change anything about anomalies, yes? But here, you are taking a scalar that was in a doublet, and now you're adding a fermionic partner that will change the anomaly unless so you have to add it such that, the anomaly of all of these have canceled, yes? So whatever you add now, better also cancels.
Mm-hmm. I understand. I have another question.
Yes.
About the Lie algebra of the whole SUSY. In this algebra, do I have to include the algebra for this whole group, the standard
yeah, but it's
group?
trivial. So it commutes with the internal symmetries. So the only non-trivial part is the supercharges with the usual Lorentz or Poincaré generators. So that's the non-trivial part. Yes. So of course the symmetries of the whole theory contain the internal generators, but those are trivial. So there are no non-trivial commutators or anti-commutators. They are factorizing essentially.
Okay.
And there's no way to do that. That's what this theorem that I told you. That's what people have tried initially in the 60s to sort of unify the internal symmetries like, you know, Gell-Mann's SU3 with spin or something, and you know, that's what the Coleman-Mandula theorem told you is not possible.
Okay, another question about the VEV of the Higgs.
Yes.
When it acquires the VEV, the symmetry will break or not?
Which symmetry? Supersymmetry or?
Yeah, the supersymmetry.
Well,
because we will have the break of the SU2 and U1, right?
Right. So the gauge symmetry better breaks, yes, because that's the electroweak symmetry breaking of the standard model. Now, the question is, does supersymmetry break or not? Yes. So we'll talk about supersymmetry breaking tomorrow. So that's okay. So the answer is that, you know, you can break the gauge symmetries without breaking supersymmetry.
Oh, okay.
Okay. But it turns out that, you know, this whole construction, in order to make it something close to realistic, you have to add supersymmetry breaking terms. Because, you know, I mean, at this point, you know, I have degenerate electrons and scalar electrons carrying electric charge, so it's clearly not realistic, yes? So I will try to explain tomorrow, you know, how to actually, you know, add those supersymmetry breaking terms such that you truly get a realistic theory, yes, where all the superpartners are quite a bit heavier than the ordinary particles, so there's a separation of scales. But then, you know, that those SUSY breaking terms will come into determining what the Higgs VEV is. So in that sense, it's not true that it's completely supersymmetric, but it's, you know, there will be some SUSY breaking present in the theory that will contribute to the electroweak symmetry breaking.
Okay, great.
Okay.
Thank you very much.
All right, I don't see any more.
One more.
One hand.
Let's do one more, and then we'll have to go to our talk.
Yeah, it's a quick and probably easy one. I was just wondering of the mass dimension of the superfields, because,
Right.
I mean, they contain scalars and fermions, so that's not really clear for me.
Right, that's a really good question. So of course, you know, let's say the chiral superfield starts out like a scalar. Yes, so it better has the same dimension, yes. But then what goes on here? Yes, there's a fermion, this is dimension 3/2. And so this theta is going to have dimension -1/2. Okay, so the dimension of theta is -1/2, yes. You know, the dimension of x is -1, yes. So this is sort of makes sense. It's almost like a square root of the x coordinate, yes. Here, two thetas are making up one x, yes. So theta is going to have dimension -1/2, yes. And then it makes sense. 1, now 3/2 -1/2, yes. And then, you know, so you will get theta squared times f. So f actually has dimension 2. Yes, and that's why, you know, it doesn't have a kinetic term, yes, because now f squared is already dimension 4, yes, so.
Okay, thanks.
You're welcome. All right.
All right.
Okay, very quick, because our talk is starting in 30 seconds.
The auxiliar, the Lagrangian SUSY not have the auxiliary superfields. So now, in Lagrangian KD, we have these contributions. So if you can say about a little bit more about it, because in SUSY Lagrangian, the F go out because I have total derivative.
Right, so what I'm supposed to do is I'm supposed to take the equation of motion with respect to F. Yes, you see, now if I take the equation of motion with respect to F, it just tells me that F equals whatever is here, m times phi plus. Yes, I can just solve it, and now I can shove it back and completely get rid of f, yes, and have a theory without the f's, but a mass term for phi plus. Okay, so that's how, the same thing with the d, yes? That's what I said, that I can integrate out the d, and there will be nothing about the d, but then there will be this potential where it's this thing squared. There will be a quartic self-interaction for the scalars.
Thank you.
Okay, all right. See you guys tomorrow.
Oh, no,
there's a discussion today, yes?
Yeah, and remember that we reconvene today at 2:15, so it's a shift of an hour.